Okay, so Graham-Schmidt has some corollaries. And so for 6.34 says any finite dimensional vector space has an orthonormal basis. And that's a direct corollary because by definition, finite dimensional means you have a finite length basis for the vector space, right? And therefore you apply Graham-Schmidt to it and you immediately get an orthonormal basis, okay? That's one. And then there is a 6.35, which says orthonormal list can be extended to an ONB. And this is just a similar statement to saying that if you have a linearly independent list, you can extend it to a basis. That was something that we proved a long time ago, right? So what you do is if you have V1 through Vm, which is linearly independent and orthonormal. By the way, if you have a list of vectors that are orthonormal to each other, then that is linearly independent. Why is that? Well, if you say C1 V1 plus Cm Vm, let's say this is an orthonormal list. Meaning that all of these are size 1 and they're mutually orthogonal to each other. And if you say C1 V1 through Cm Vm add up to 0, then you can take this and do an inner product with any Vj, and because it's mutually orthogonal, the only thing that has a non-zero thing is Cj Vj has to be 0, but then Vj is 1 because it's orthonormal, so you end up saying Cj is 0. And this is for any Cj, so that you end up saying C1 through Cm are all 0. So we know that this is already linearly independent. And if it's linearly independent, then you can now extend this to a basis, V1 through Vm, and then say U1 through UK. Now it's a basis. And once you have that, then you can apply the Graham-Schmidt. And if it's already orthonormal, then Graham-Schmidt doesn't do anything. So these don't change. But now these portions will, by the process of Graham-Schmidt, this is going to be W1 through WK, so that this entire thing is now an orthonormal basis. So that's a simple corollary of the Graham-Schmidt procedure. And lastly, there is the Schurs theorem. Schurs theorem for linear algebra. Now, there's a more famous result of Schur, which is something called Schur's lemma for representation theory. That's something that you learn in grad school. And because representation theory also deals with linear algebra a lot, people get confused. But this has nothing to do with the famous Schur's lemma. This Schur's theorem for linear algebra says the following. For a finite dimensional vector space V over C. So we're working on complex numbers. Any T in an operator over V has a basis B, an orthonormal basis B, such that the matrix of T represented using this basis is upper triangular. So later we're going to use this for proving the spectral theorem. It's about being able to diagonalize certain class of matrices. Now, if you look at this statement, this seems to be something that we've already done before, and there is 5.27, which is like almost what this is claiming, except the only difference is over there, the basis B wasn't required to be orthonormal. Okay? So 5.27 says such B, not necessarily ONB, exists. So now the proof is you take that basis, so let's call this B prime. Okay, so find a basis B prime so that the matrix of T under this B prime is upper triangular. Now, however, this we had an equivalent condition which says that if this is V1 through Vn, then being upper triangular was same thing as saying that T of span of V1 through Vk is in the span of V1 through Vk. In other words, this span of V1 through Vk is an invariant subspace of V under T for any k. If that's true, that's same as saying that this is upper triangular. That's another theorem that we proved before. Now, what happens is that if you look at the Gram-Schmidt procedure of defining UK, you see that UK is defined as VK minus something V1, something U1, something U2, over, you normalize that. So whenever you define your UK, it's always made from the previous guy. So it's just that if you look at what the Gram-Schmidt procedure is doing, the new vectors are always made from the previous one, so that this relation of this being an invariant subspace still holds, because it's always true that span of this is same as span of U1 through UK. The Gram-Schmidt preserves this identity, because you're always making new vectors by making use of the U vectors and the previous ones. So these two spans are the same. So this T of this is same as T of this guy, which is inside the span of this, but which is same as that one. So the procedure of Gram-Schmidt says span of U1 through UK is an invariant subspace of V under T, and therefore even if you use this new basis B obtained by Graham-Schmidt, the matrix of T under this B will also be upward triangular. Okay, so that's the proof.